Dear friends, this is my tutorial 13. So in this video I'm going to tell you how to execute AIMD calculation in VASP and analysis with VASPKIT and VMD. So this is the system, FENC system. I'm going to tell you how to prepare input file and do the AIMD simulation using VASP. So this is FENC system. So why we want to do AIMD? So this is to check the thermal stability of the catalyst. So basically people will do 300K and 500K and 900K. You can do this three kind of temperature, so you can see your stability of your catalyst. So then we can plot that AIMD results produced by VASP using a VMD and VASPKIT. So we can also plot the figures for bond length waste time and RMSD waste time, and people also will plot total energy waste time and also the temperature waste time. So this kind of the plot the people will plot. So I will tell you how to plot these things later. Now I will show you the in-car file for AIMD simulation. Now I will show you the in-car file for AIMD simulation. So this is the AIMD input file for my AIMD simulation. So first I will show you the parameter for in-car file. So this is the in-car file for AIMD simulation. So this is the system name, so you can give your system name. So this is based on the computer core NPR. Based on your computer you can give this value. So this is the general parameters. So here we need to I start 1 and I charge also 1, precision normal. So it is enough, and grid also false. So LTL auto you can give. So important things, isometry you can put 0. This I mentioned what are the things. Okay, these are the important things, so you need to check once. So IDI pole also 3. This also you can give n right equal to 0. So these are the general parameters. So then we can see the motion, cell and geometry optimization, relaxation. So here you can see IBRON you need to mention 0 only. So here I mentioned 0 for MD, 2 for that conjugate gradient optimization. So these are different kind of things. So you can give IBRON 0 for molecular dynamics, ISIF 2. Here only we going to relax the atoms only, so not in the cell. Then you can give NSW 500. This is the how many steps you want to perform. Okay, so if you see here maximum cycle of optimization. So if you see here, so I mentioned 5,000 steps equal to 10 picosecond. So that means with potium 2, if you are if you give potium 1, so 1 into 5 into 5, so the 5 picosecond will do the calculation. So basically I will use potium 2 5,000 cycle, and that means 10 picoseconds. Okay, so basically if you want you can also give 6,000 here, because in initial 1,000 steps you may see some more fluctuation. So to overcome this you can maximum put the 6,000 steps. So then the initial 1,000 steps you can ignore and use other 5,000 steps for your publications. Okay, you can also do like that. And I already told you potium equal to 2. I always mention 2 only. Some people also will use 1. So if you use 1, it will get the 5 picoseconds like that. So then you can mass equal to 0. So 0 is NVT ensembable. This you have to mention. So an MD algo is there's no C over thermostat. We have to use this one only. So here you shall see the time initial. You can initial temperature 0 Kelvin. So time beginning is 5,000 step, and the time not time beginning, temperature beginning 500 Kelvin, and the time temperature end also 500 Kelvin. So if you want to give other temperature, you can want to give 900, you can give here also you can give 900. That means your calculation will for 900 degree Kelvin temperature. So these are the important. You can give also NB log 1 for dynamics calculation. And also here see the important SEF parameters. So NCAT I used always 400. So then I spin 2 so all go fast. So if you use very fast, it may not converge, so you can use fast all go is, I think, is best for this kind of calculation. NLEM equal 100. This is, you can also give maybe 1000, maybe I think 100 is enough, that minimum, that SCF cycle. So and EDIF I used here 110 to the power minus 5 0.5, so we can use this is enough. Then ISMER equal to 0 and sigma equal to 0.2, this is enough. Then functional we will always use GGA and PE. So this is the in-car file for molecular dynamics simulation. So I will share this file to you. You can use it, do molecular dynamics calculation and perform. So then we will see the K-point file. So this is the K-point file. I always use K-point file for molecular dynamics is gamma point 111, because if you use that higher level of K-point, so it will take a lot of computational time and computational resource also. That's why I use always 111 for molecular dynamics simulation. I think it won't affect that system, I think so. So you can also try to use this kind of small K-points. Then I will show you the postcard file. So this is the postcard file. So this is the carbon 66 atom, nitrogen 4 and Fe1 atom. This is the postcard. I will show you the structure using Vesta. So this is the structure. So this is actually optimized, so energy minimized structure. So actually before you do the molecular dynamics, you need to minimize your structure. So then take that file for the molecular dynamics simulation. Then port car file. So here I use 3 kind of port cars, so I will show you. So here carbon first, second is nitrogen, third one is Fe atom. So this is the postcard file for the corresponding postcard file. Then you can use your submission script to do the calculations. Okay. So that's all the input file for AIMD simulations. So actually I already submitted this calculation and completed. This is the graphene FEN for AIMD simulation. So next video I will make you how to get the result from that, the AIMD output files. Okay, so I will show you how to get the different kind of data from there. Okay. Thank you for watching. If you like my content, please like, subscribe and comment and share, and also please click bell icon for my future updates. Thank you for watching. Thank you for your valuable time.